In this question, we need to solve this system of simultaneous equations, and we're going to do it via elimination in this video. There are other videos using matrix row reduction and using substitution to approach this exact problem. So when using elimination, we're going to start by labeling our three equations, which makes it easier to refer to them. And we need to find some way to eliminate one of the variables to start with. Now, looking at this, I could multiply the x to get rid of the x's, I can multiply the y to get rid of the y's, or the z to get rid of the z's. Does it really matter which one we choose? Not particularly in this case. I'm going to choose x just because I can multiply 1 to get 2 and 4, and I can multiply 2 to get 4. Whereas with y, yes, I can get 1 to 4 and 1 to 3, but I can't really get 3 to 4 very easily. And similarly, I can't really get the 2 to the 3 very easily. It would involve more steps. So I'm going to eliminate x. And the way I'm going to do that to start with is by multiplying, taking two lots of equation 1 and taking away from that equation 2. I'm going to do two lots of this equation, take away that. So 2x take away 2x is no x's. Two lots of this will be 6y. Well, you know what? I'm going to write this all out because it's just going to get very confusing, isn't it? So let's do two lots of 1 first of all. That's going to be 2x plus 6y take away 4z equals 6. And underneath, I'm going to write equation 2, which is 2x minus 4y plus 3z equals 5. Now to eliminate those, I'm going to take them away. So 2x take away 2x is 0 x's. 6y take away negative 4y is 10y's. Negative 4z take away 3z is negative 7z. And 6 take away 5 is 1. Now I have one equation in y and z, but I still have two unknowns, so I need another equation in y and z. Let's call that one equation 4. And now to do that, I'm going to combine equation 3 with something. In fact, I'm going to combine it with equation 1 again. Let's do that. So this time I'm going to do 4 times equation 1, which is going to give me 4x plus 12y take away 8z is equal to 12. And underneath that, I'm going to write down equation 3, which is 4x plus y minus z is equal to 6. Again, I'm going to subtract because I have the same number of x's here. So 4x take away 4x is no x's. 12y take away a y is 11y. Negative 8 take away negative 1 is going to be negative 7z. And 12 take away 6 is equal to 6. And we'll call that one equation 5. Now I have two equations in y and z, equations 4 and 5. I can solve them simultaneously. So I'm going to write them down. 10y take away 7z equals 1. 11y take away 7z is equal to 6. And I'm going to do the subtraction here because I have the same number of z's in both equations. That gives me minus y equals minus 5. If minus y is equal to minus 5, then y is equal to 5. Now I know that y is equal to 5. I'm going to substitute that into either of these equations. So sub it into 4, for example, and I'll get 50 minus 7z is equal to 1, which means z needs to be 7 to make 50 minus 49. And finally, to find x, I need to substitute into one of my original equations. Doesn't particularly matter which one I do. So I'm going to substitute it into that last one, 4x plus y, which is 5, minus z, which is 7, is equal to 6. So 4x is equal to 8 and x is equal to 2. That is, my answers are x is equal to 2, y is equal to 5, and z is equal to 7. Which is exactly the same answer as we get through matrix row reduction or through substitution. I will point out this one was relatively straightforward at this step here because we had minus 7z in both of them, so we didn't need to do any multiplication. We obviously might have to scale one of these or both of these equations at that stage so that we could do this step here.